Hello and welcome back. We're beginning our second day on volume, but first let's do a review of surface area. Now we're going to investigate today the difference between the formula for the volume of a prism and a cylinder and the volume of a pyramid and a cone. But first let's remember what the relationship between the surface areas of those two shapes were. So over here we have a rectangular prism. We're looking for any shape that's not a rectangle, but they're all rectangles, which tells us it has to be a rectangular prism. So we're going to default to the bottom surface as our base. So we have 10 and we have 8. Now if we're going to try to find the surface area, that's the area going all the way around the entire figure on all 6 faces in this case. So what's helpful we learned was to look at the net. So the net is a 2-dimensional representation of the 3-dimensional polyhedron, and if we found the surface area of all 6 of these faces here combined, that would give us the total surface area of the 3-dimensional shape. So our formula goes something like this. So our surface area is equal to the 2 bases plus the perimeter times the height. Well, the perimeter times the height is going to be our lateral area. So what we end up doing is finding the lateral area here, and then we add our 2 bases to it. So first we found our base. We just multiplied the 2 dimensions of our width and our height, assuming those two are perpendicular to each other, which gave us 80. So the area of this base here is 80. Well, that means the other base is going to be 80 as well, right? So we're going to add those two 80s together, which is 160. And then we're going to add the perimeter times the height. Now, the reason we're finding the perimeter of the base, that's the distance all the way around, is that's going to be the same as the width of the lateral area. So 10 and 8 is 18, and then another 10 and 8 would be another 18. So that's going to be 36. So this total perimeter is 36. And notice how that's the same as the width of the lateral area. Then we multiply by the height. Now the height is going to be the distance between our 2 bases. In this case, that would be 12. So that's going to be the height of the lateral area. So 36 times 12, that's this perimeter times the height, right? That's going to give us the lateral area, which in this case, I think is 432. Okay, so 432, that's going to be this rectangle of all 4 of these rectangles going around combined, okay? So we take our 2 bases of 160 plus our lateral area, which we said was 432, and that'll give us a total surface area of 592. Now, the next part is when we look at the relationship between the rectangular prism and the rectangular pyramid. So let me drag that up here. So remember, a pyramid, instead of going to another congruent base that's on a parallel plane, now we're going to have lateral, it's going to go to a single apex, vertex, which we call the apex, and that's going to have lateral surfaces or lateral faces that are triangles instead of rectangles in this case. So we're looking for a shape now that's obviously a pyramid. That's not a triangle, and so that's going to give us our rectangular base. Okay, so the math is exactly the same. We still have a base of 80, right? But what changes to our lateral area, and we only have 1 base instead of 2 bases, right? So this base here, that's nice. There's no base on the top, right? So only 1 on the bottom. And instead of having rectangles going around for the lateral area, we now have triangles. So how does that change our formula, and how does that change the net? So now instead of looking for the rectangles, we're looking for a bunch of triangles, which would have half the area. So we have to do the perimeter times the height divided by 2. So it's going to have half the lateral area and only has 1 base instead of having 2 bases. So altogether, this is going to have, I'll go ahead and show you the work. So we got the same, it's kind of annoying. We got the same base there. The perimeter is still going to be the same. We still need to know the perimeter and the area of the base, right? Then when we multiply the perimeter times the height, we then divide it by 2. So that's the only difference here. Also, we call this the slant height because we need to know the height of the triangles, not the actual physical altitude of the triangular pyramid. Now, for the volume today, we're going to be using the actual height, which is going to be orthogonal to the base, meaning it's perpendicular in all directions, instead of the slant height, which is what we used to use when we were dealing with the area, which goes with the lateral area, the triangles going all the way around, okay? Lateral area in this case would be 12 times 36 divided by 2, which is going to be half of the lateral area for the prism. So notice that that's exactly half, right? And then the surface area, when we add the perimeter times the height divided by 2, we now have to add our 1 base, which is 80 more than that, which notice this value is half of this one as well. So the formula for the pyramid, surface area of a pyramid, is exactly half of the surface area for the prism that has the exact same height as the slant height in this case. All right, so notice it's half because we have 1 base instead of 2, and we have a perimeter times the height, and which were rectangular lateral area. Now it's the perimeter times the slant height, which is slightly different, divided by 2 because we're dealing with triangles. So the relationship between the surface area of a prism and a pyramid is exactly 1/2. So now we'll move on to volume. This is probably my favorite and the most aesthetically pleasing object that I've made in Smartboard and SmartNote. So yeah, I hope you guys enjoy this. It was a ton of fun for me to make it, and it already looks intriguing. So what is the ratio between the volume of a pyramid and a prism? So remember, on a prism, they're very, very easy. So yesterday's assignment should have been really simple. All we do is we find the area of the base, right? In this case, that would be 3 times 3, which is 9, right? Then we multiply it by the number of layers that we have. So the first layer is just going to be times 1, right? So how many cubic centimeters are filling up this cube right now? Well, there's 9 of them, right? But then we have to look at our height, which is how many layers do we have altogether? In this case, we have 3 layers, right? So it would be 3 times 9, which is 27. Now the question is, so there are 27 cubes filling that in. The question is, how does this differ when instead of filling it up like a prism, we fill it up as a pyramid? So it's going to go to a single point up here instead of going to a congruent base that's on a parallel plane. So whenever we fill up the first one, so dope. Oh my gosh, look at that. You can see that it's not filling up the entire thing, right? There's this gap that's starting to form. So instead of having 9 cubic centimeters like we would have on the first layer over here, we have less. But how much less? Well, not a whole lot, but there is this gap, this ring that's forming all the way around the outside, right? Then as we fill our second layer over here, that would give us 18 altogether. But then whenever we fill up our second layer here, going to the red line, so awesome. You notice now it's even less, right? It maybe, I don't know, maybe about half of the total volume in the second layer that we had over here for the prism. Okay, and then once we fill up our third layer, here it's not changing, it's still another 9, but over here we have even less. Maybe it's 1, or maybe it's less than 1, right? So what is the total volume of the pyramid compared to the total volume of the prism? Now when we were talking about surface area, we found out that there was this nice relationship of 1/2, and I could very easily show you why it was 1/2 by analyzing what happens with the net. We have 1 base instead of 2, right? So 2 bases, 1 base, and then our lateral area here, instead of being a rectangle, to triangle, so it's exactly half, right? But when it comes to volume, it's not really that easy to see what that ratio is. So I just want you to take a moment and think, what do you think the ratio is for the surface area of the pyramid, or sorry, the volume of the pyramid to the volume of the prism? Do you think it's half? Do you think it's more than half? Do you think it's less than half? So if you want to pause the video and think about it, think about a fraction or a ratio that you want to guess, and see if you get it right. All right, so unfortunately there's no real really great way to prove this. So what we usually do in class, if back when we used to meet in person, is that I would get out sand and some geometric solids that were hollowed out, and they would be both the same dimensions, except one would be a pyramid and one would be a prism. And what we would do is we would take the pyramid and fill it up with sand and scoop it and pour it into the prism and see how many times we could pour it in to the prism until it fills it up with sand. And once we fill it up the first time, I guess we'll kind of do it together here. The first time that we pour it in, a pyramid's volume into the prism, it will fill it up about that much, which looks like half, but it's actually a little bit less than half. And then the second time that we would fill it up, it would fill it up to about that, which would, oh wait, no, of course, actually the first one would actually fill it up to that layer. Yeah, that makes perfect sense. So the entire volume of this pyramid would fill up the prism right there. Isn't that interesting? And then the second time that we would pour the sand in for the pyramid, it would fill it up to the second layer, which is pretty interesting. And then the third time we would fill up the volume of the pyramid with sand and we pour it into the prism, it would top it off exactly to the very top. So you probably figured out what the ratio is. I didn't even plan that. That was kind of cool. But the ratio is actual ratio of 1 to 3. So the formula for the volume of a pyramid is 1/3 of the volume of the prism with the same base and the same height. So instead of having a volume of 27 cubic centimeters, this one over here actually only has 9 cubic centimeters, which is interesting because that's exactly the same as one of these layers, which is pretty cool. If you look at this volume and this volume over here, those two are exactly equal, which I didn't even plan that, but it's really stinking cool. So you can see where all that stuff that was missing on the outer edge here, all of that would have been able to fill up the rest of this pyramid, or at least the last 2/3 of the height of the pyramid would have the same volume as the base, right? No, maybe that's not true. But it would altogether have the same volume as this first layer of the prism, which is really, really cool. So our formula for the volume is base times height divided by 3. So just like we did for the prism, base times height, but now we have to simply divide it by 3. So when we had surface area, it's basically 1/2 of the surface area of the prism would give us the surface area of the pyramid, and for volume, it's 1/3, which is pretty stinking cool. All right, so we do need to look at units and their dimensions again. And the reason I'm going to point this out is because right here we've got 3 different units to 3 different dimensions. So our base was an area, so it was centimeters squared. Our height was a 1 dimension, just the height here, centimeters. So that's centimeters to the first power. And then the volume is cubic centimeters, which would look something like that. So we need to go over this real quick. So length, for instance, like if we had 7 feet, the units are, it's just 1 dimension. We're only measuring the width or the height or the depth of something, right? But only 1 dimension at a time. So the units would be in a unit of 1 foot, right? And there would be 7 of them altogether. Now, if we added another dimension, so not just a width, but also a height in this case of, let's say, a width of 7 feet and a height of 4 feet, then now our units are going to be feet squared, and we're talking about an area. So we went from 1 dimension to now 2 dimensions. And then when we add a third dimension, like a depth in this case, we still have a width of 7, a height of 4, and now a depth of 1. So now our units are going to be cubic feet. And the way that we would calculate the volume would be the base times the width times the height in this case, right? So all we're doing is multiplying by an additional unit in each case, and so we notice that our units actually go up in their power as well. So we go from foot to the first power to foot squared to cubic feet, right, to the third power. So the same thing, we just have to be careful when we're talking about a area, right, a 2-dimensional unit, a distance, which is a 1-dimensional unit, and a volume, which is a 3-dimensional unit. So those do matter. They're talking about 3 different things: 1-dimension feet, 2-dimension area, 3-dimension volume. One more thing I want to teach you is the difference between right and oblique polyhedrons. So I think I mentioned this. This is the first time I've actually ever taught this. It's a little bit above the scope of this course. There's nothing like this that shows up on the test, but I think it's kind of cool, and it's kind of get your brain going a little bit. So we have always used and worked with right polyhedrons, but there's this other thing out there called oblique polyhedrons, which you can probably guess is the funky one over here. So right polyhedrons, when it's a triangle, means that the apex, which is the tallest part of a pyramid, is going to be directly centered above the center of the base. So it's orthogonal to the center of the base. So perpendicular, just going in all directions, we call it orthogonal. So if something is perpendicular to a plane, we would say it's orthogonal. If it's perpendicular to a line, then we say, or 2-dimensional shape, we would say that it's just perpendicular. All right, so if it's centered like this, kind of what we would think of like a regular polygon, but this would be like a regular triangle or a regular pyramid, that's because all the lateral areas are going to be congruent whenever this happens. But what about when we take this apex and we move it off the center here? So this is the same dimensions of the base. All I did is I moved it, kind of squished it over. But notice it still has the exact same height. So these measurement lines show us that the apex is still the exact same height above the base, at least the plane for the base, right? So it has the same height, but now notice what happened to our slant height. So we would use the height for volume and the slant height for the surface area. The slant heights for the lateral surfaces are all going to be congruent whenever we have on a right a polyhedron, but over here the slant heights are going to be different. So notice that this triangle, which if we had to find a surface area, would have a smaller slant height than this one, because this one has to be elongated because we moved the apex off center. So notice if we dropped a perpendicular from here, it's no longer going to be centered in the center of our base. So this is not a right polyhedron. Excuse me, it's an oblique polyhedron. So our actual formulas for the volume of the polyhedrons, whether they're right or oblique, are going to be exactly the same. So if these two rectangular pyramids have the same base, area of the base, and the same height, physical height to the apex, then they will have the same volume, which is interesting. This one might look bigger, but it's actually just taller and skinnier, at least taller in the slant height dimension, not the actual physical height. And then this one might look a little shorter and fatter, but it's actually going to have the exact same volume as this one over here. But when it comes to slant height, as you can probably guess, it doesn't work out quite that well. We would actually, I believe, we have to find the surface area of all four of these because they have different slant heights. I suppose if we knew the average, that would change, but we would need to know all four of those. And the reason for that is if we took this apex and we moved it way off the edge, there's no limit to what the surface area would go to. They would all have I believe they would all have the surface area would just keep increasing and increasing and increasing, because their slant heights would just keep increasing and increasing without bounds as well. So that's my logic to say that the formula kind of breaks down whenever it comes to calculating the surface area of an oblique polyhedron. All right, so that's enough of that. You will not see any of this, but I think it's kind of cool and interesting to think about it, and I got to talk about infinity, which makes me really happy. Unlike Gregor Cantor, who lost his mind in an insane asylum. All right, so number one, that was it. So if you guys want to get out your assignment, let's go ahead and get started and look at number one. So on number one, we want to find the area of the base first, just kind of following the same procedures as we did before. So this is a triangular pyramid. It's not a triangular pyramid, sorry, a rectangular pyramid. Notice that we have triangles for the lateral area, so the only one that's not a triangle is going to have to be our base, which is this square on the bottom. So our base, the area of the base is going to be 8 times 8, which is going to be 64 inches squared. The height is going to be the physical height from the dropped orthogonal to the apex. So from the base to the apex, the direct shortest distance there, which would be orthogonal, is going to be 10 inches. So notice we're not using the slant height. We don't have to calculate the slant height like we did for surface area. We don't have to do Pythagorean theorem like 4 squared plus 10 squared and then take the square root of it. We're not doing that for volume. That would be for surface area when we would know the area of the lateral surfaces going around. So for the volume, we just do the base times the height divided by 3. So we'll go ahead and launch my calculator real quick. But that's going to be... Don't think that I can't divide that evenly by 3, so I'm going to have to use my calculator. Sorry. Because we're going to get... is it big enough for you? Can you see it? Because we're going to end up getting it probably a repeating decimal. All right, so we're going to do our base of 64 times 10, which is just 6,400, or 640. Then we're going to divide that by 3, which is going to give us 213.3 repeating. So our volume is 213.3 repeating. And notice we just put a bar above the 3 if it's repeating like that, because it's going to be 1/3 as what the fraction ends up working out as. All right, and notice this is in inches cubed. Okay, number 7. So on this one, I didn't make it look pretty. I know. That one looks good. This one needs to be redone. So our base is 13. I guess they're assuming that this one is a square base, so 13, because they don't give us another dimension, so 13 squared for the area of the base. So we're going to do 13 squared, or just 13 times 13, which is 169. Okay, so 169 millimeters squared. Our height, now on this one, notice they give us the slant height. We don't want the slant height. We want the direct distance from the apex all the way down to the base. So we're going to actually have to use the Pythagorean theorem for this one. So I'm going to go ahead and drop the height, which is what we're actually interested in. Actually, let me change the color first. That way we can see it better. Okay, so I'm going to drop a perpendicular, so orthogonal to the base, and so I'm going to mark it orthogonal by putting a right angle there. Let's see, struggling today. All right, and then the next part here is going to be this length on the bottom. Now this triangle that we've actually formed here, the slant height or the hypotenuse of this triangle is going to be 12.5. We know it's a right triangle because it's orthogonal to the base. That's how we constructed it whenever we drop that perpendicular. So we're actually going to have to use the Pythagorean theorem in order. I should have had all this pre-made, but we're going to have to use the Pythagorean theorem in order to solve for the missing part. So if this is 13, this we're going to assume is a right polyhedron, so it's not oblique. So that means that the center of that the apex is going to be directly above the center of the base, which means that this is going to be half of the distance of 13. So we kind of had that assumption all along, but we're just making it kind of formal now. So this would be 6.5. Change the size real quick. All right, so we'd have 6.5 here, and then 12.8 for our hypotenuse. So what we want to solve for is the height. So to find the height, what we need to do is the Pythagorean theorem. So I'm going to go ahead and get that out. And we're solving for a leg, so we're going to end up subtracting. So we have 12.8 squared. So that's squared minus 6.5 squared. And then we're going to have to take the square root of that value because that's going to be the height squared. So caret 0.5, I'll do to the find. All right, so 11.03 is going to be our height. And that's millimeters because we're only doing, it's just a length, right? So one dimension distance. Now that we have the actual height instead of the slant height, you do have to be careful when do you use which one. Remember, slant height is with surface area because we know the area all the way around the triangles, and the volume is just going to be the height because it actually doesn't matter if it's oblique or not, as long as we just need to know how high is the apex above the base, the perpendicular distance between those two. All right, so the volume, we just multiply the base times the height divided by 3. So I already have all the precision here, so this is a trick. I'm going to go ahead and multiply that times 169. Instead of using the rounded value of 11.03, if you're wondering how I get some of my decimals that are a little bit more precise than what you've got, it's because you might have been using rounding figures like 11.03, which was an approximation. But I'm going to use all the precision the calculator has, multiply it by 169, and then divide that by 3. Which will give me 621.118. So 621.18 millimeters cubed. All right, number 11, we want to find the area of the base. Well, it looks like they give us the diameter of 14 using the measurement marks here. So the radius would be 7, then we would do 7 squared, which is 49, and then it's 49 pi. So 49 pi feet squared. So if you want to know how many actual feet squared it would be, we'd have to multiply 49 by pi. But you'll notice every time we do that with pi, we're always going to have a decimal, and so I like to leave it in terms of pi so that we don't have anything. We don't lose any precision. So if I convert that, we'd have a decimal. But 49 pi is exact. This would be an approximation, which is not exact. All right, our height in this case, they gave us the right one, so we don't have to do the Pythagorean theorem. That will get annoying. You'll have to do, I think, 4 of them, so get over it. All right, so 24 is the height, and then the volume. We would do base times height divided by 3, so 49 pi. So let me just do 49. I'm going to leave the pi out and just put it back in my answer when I'm done. So 49 times 24 divided by 3. Could have done that in part, but it's going to be 392 pi feet cubed. So I put the pi back in. If I would have put it in here, it would have just left it in terms of pi anyway, so it wouldn't have mattered. So if I did 49 pi times 24, but maybe your calculator would automatically go to a decimal instead of giving it in terms of pi, right? So your calculator might have given it out as that. And if that did happen, all we can do to get pi back out is to divide it by pi, and then let's get us back where we started, then just leave it in terms of pi. So 392 pi feet squared. I'm sure some of you guys are using the calculators on your phone, which don't always simplify. All right, 15. So again, this one actually is oblique, so I guess I said we weren't going to have any, and then I threw one at you. So anyway, the formula for the oblique is exactly the same for volume, but for oblique polyhedrons, the surface area cannot be calculated unless we know the slant heights of all of the lateral surfaces, which would be kind of annoying to have to do it that way. But anyway, the area of the base, we have a radius of 10, so that's going to be 100 pi squared, 100 pi meters squared, sorry. The height is the height from the apex directly down to the plane of the lateral of the base, which is going to be 12, so 12 meters. And then our volume is going to be 100 pi times 12 divided by 3. So if I just do 12 divided by 3, that's going to give me 4. So 4 times 100 pi is going to be 400 pi. So 400 pi meters cubed. All right, 19. So this is kind of volume by decomposition. So we have a cylinder and a cone on top. So we're going to find the volume of the cylinder and then the volume of the cone and add them together. So base is going to be 9 squared is 81 pi. I think this is in Times New Roman. Yeah, I can tell the font's different, not the Arial I usually use. Then our height for the cylinder is 15. And then the volume is going to be 81 pi times 15 divided by 3. If I do 15 divided by 3, it's 5. So 5 times 81 is going to be 160. No, sorry. I'm just going to skip right to the answer. 1215 pi. Okay. And then for the cone's going to have the same base of 81 pi. So all we have to do is 81 pi times the height of 12, then divide that by 3. Which when we do that, we should get a volume of 324 pi. So now we have the volume of the cylinder and the volume of the cone. So all we have to do now is add them together, which will give us a total volume of 1539 pi centimeters cubed. Notice when we are finding the volume of the cylinder, we do not divide it by 3, but when we find the volume of the cone, just like a pyramid, we end up dividing it by 3. All right, 21. I think this is the last one I'm going to do with you. Yeah, it is. All right, so on this one, the first thing we have to do is find the actual height there. I think, yeah. No, actually, see, they tell us the volume is 1,500 units cubed. So the first thing we want to do is find the area of the base. Okay, so 15 times 15, so that's going to be 225. So if we have the base is 225, right, that gets multiplied by the height and then divided by 3 to give us the volume. So if I want to solve for the height, which is x in this case, I have to do two things. So first thing I have to do is multiply both sides by 3. So I'm going to do that first. Okay, so 3 times the volume. That would be kind of going from a pyramid to a prism. So if we had the prism, which had 15 by 15 and the same height, then we'd have 3 times the volume, right? That's basically what we did. This is kind of cool. And then we'd have the base times the height. Well, we know the base, so then we can divide both sides by the bases, the area of the base, and that'll give us the actual height. So let me put that in the calculator so you can see what we're going to do. So the first thing I'm going to do is take the volume that we were given, which was 1,500, and I'm going to multiply it by 3. And that's going to take it from a pyramid to a prism, because it would have 3 times the volume, right? Which is just a formula of base times height, which is a lot easier to work with. Then I'm going to take that and I'm going to divide it by the base area, which is 225. That's the volume in each layer, in other words, and this will tell me how many layers I have to get it up to 4,500, which would be 20 layers. So the height here has to be equal to 20. All right, it can be a little tricky, but I think you'll be able to figure it out. So I will see you guys later.